In this episode, we explore our same graphing context, but now for a circle. Zoe and Gisele will explore what the graph of a point's journey around a circle looks like that relates the height of the point as a function of its distance traveled.
Create a graph that relates the height of a point to the distance traveled by the point around a circle.
So we'll just start it like we always do with height and distance. Ooh. So you said distance is and then height, right?
We'll still set this as 0.
And then with no side lengths, it's just going to look like a sine curve. Yeah, it's just going to be this.
Okay, it's cute.
That was good.
This is our graph.
Okay. Can you walk me through the thinking for this graph?
Sure. So starting at 0 again, we made this x-axis 0. As there's no side lengths to increase by, it's just going to generally increase. So as you're traveling up the circle, you're just getting, your distance is still being traveled, but your height is increasing. And then basically like right here, it is going to be the same as like up here at the very top of the circle. And then you're still traveling distance, you're decreasing as you go around this way. And then once you reach the very bottom of the circle, that'll be like here, it's going to start increasing again. But since there's no set lengths or sides, it's just going to be one continuous curve.
Okay. Anything you would add to that, Gisele?
I think it looks like the square graph, but with no points.
Could you say a little more about that?
Like, just use red. If I have red as the square graph, it was like shoop, shoop, boom, boom, boom. It's like that. That's the square graph, I think. But it just rounded out all the curves because the same thing's happening. Like as Zoe said, if you do both of them, like for this one right here, you're increasing distance and height, and then for this, you're increasing distance and height, and then this one, you're decreasing height but increasing distance. That happens right here. It's just that the reason we have flat lines and a like squares because this is a constant, but you don't have any lines in a circle. So yeah, it pretty much looks like a squares graph, just if you rounded out the curves and ignored the constant lines.
Yeah.
That is a great observation. Is there anything you notice about like why you think there are differences in the shapes of these graphs, Zoe?
I think that since it is a circle with like no defined sides, I think I mentioned that earlier, that just accounts for the roundedness of the graph.
Okay. Could you say a little bit more about that? Sorry.
Yeah, so with any of the polygons that we graphed, the segments represent like a segment on the shape. So, and then like when there was like a sharp corner, like right here, that's when it would change to either constant or another segment. There's no sharp corners on a circle, so there's no indication of like a sharp change in segment, so no like specific change in slope. So then that just means that like the curved line, it just represents like a gradual like growth and then decrease, rather than like on the square graph how it's like growth, then like a sharp change to constant, then a sharp change to decrease. There's none of that on the circle graph.
What do you think about that, Gisele?
I agree because I think she explained it perfectly. Like the whole definition of a circle is that there's no sharp corners and it's just one continuous line. And well, any other shape, whether you have 100 sides or 3,000 sides, there's a side. Well, a circle doesn't have any set sides of everything. So therefore, like, the graph is going to have to be just one continuous line, and rather than in segments, because there's no sides to it.
Okay. What is happening at the end of these segments that's not happening for our circle?
Like at the corners?
Mm-hmm.
The corners are like a change in direction of movement or height. Like it's so like we said again with like this being 0, I'm gonna change colors. You go up, so you're increasing in height, increasing in distance, and then immediately at this corner you're stopping your increase in height, but you're still increasing distance. And then at this corner you're immediately switching to start going down, which is a decrease in height. On the circle, there's no sharp corners or like turning points, so there won't be any like turning points represented on the circle graph.
So we've said that at these segments, the point's height is changing in some way, right? What does that mean for the point's height as it's traveling around the circle?
I think we said this, but there's no segment on the circle where the height is not changing. So it's reflected in the graph because like there's no flat lines on the graph. So no matter what, the point's height is increasing. When you get to the top of the circle, it starts decreasing. Again, when you get to the bottom of the circle, it starts increasing again.
Okay.
I think that shows a clear depiction of everything.
In this episode, we worked together to create a graph that we believe represents a relationship between the height and the distance traveled by a point moving counterclockwise around a circle. After drawing the graph, we worked to describe why it has this shape. We made a few key observations. First, we noticed that there are no segments where the height isn't changing. This was clear when compared to the graph for our square task. We also noticed that there are no corners, but we struggled to really describe what is happening at these corners that would thus not be happening on our circle graph.